Okay. um. Oh no, OBS has changed. Oh, here it is. Cool. Okay. Very good. Hello, hello, hello. Thank you for the AV is working. Sweet. Hello, everyone. Welcome back. Um, cool. Hello, hello, hello. Okay. Things seem to be happy. Cool. How are you all doing? Um, lots of crabs. I'm still a little bit under the weather today, and I clearly was yesterday. Sort of in retrospect, some explanations really were not their best. I apologize for that. It's a bit of a like a when you're on a university term, it's a bit of a the show must go on kind of vibe. Um, and so I'll put together what I'm able to. And there's always if you sort of need and very reasonably may desire some like supplementary explanations and understanding. The 22T3 lectures are actually good for an extra reason, which is if I open them up here. If I go to say lecture 3 week 2 Monday from 22T3, so the original term, and hopefully I don't get a YouTube ad. They are usually maybe they are. Yeah, they are. Yeah, there's that YouTube ad. Fantastic. All right, let me go down, please. They're usually time stamped. This wasn't my amazing effort. This wasn't even like a tutor's amazing effort, as it usually like most often is. This was actually a student's amazing effort from our first term. They went through and provided timestamps because they wanted the timestamps themselves anyway, and so sort of donated these to the course. So I think that's been helping students every term since. If you go back and thinking, oh, I didn't really get what was going on with that, like find the mean thing, or I want to see that explained, the same kind of context, content rather, but explained, just slightly differently or in a slightly new way. It's really convenient to come back to this kind of thing and have a look through, especially with these timestamps. So I highly recommend that if you're if you're feeling confused about things, which is totally cool. Okay. So as always, I see we're already kicking off on this, which is fantastic. But I'll say it explicitly as well. Anyway, any questions? Feel free to start them off, keep them coming. And so we've got. Are we going to talk about derive in a future lecture? Yeah. So derive is it falls under the topic of macros in Rust. In fact, also this is a helpful thing to know. If you go to the course outline over here and to course schedule right here, we get a rough idea. We've sort of got a rough explanation of the kind of things you can expect to see during the course. Meta programming is in week 7. Meta programming here, and meta programming basically we're looking at macros in Rust. But also we'll end up looking at a couple other languages as well, or mostly C, for comparison's sake. And so yeah, derive falls under the macros. So we'll understand a little better what derive is, and like from a more fundamental level, how does it work, and how are you able to, let's say, even build your own derive macros. In theory, it's actually too difficult for the scope of the course, but we'll talk about how you would go about finding that out, and if that's what you were particularly interested in. But we're not going to force you to do it because it is actually quite difficult generally. But until then, we're basically just going to use derive and sort of hand wave the details away. If it says, hey, your type needs this thing, add this derive, just follow the compiler's advice and add that. And you'll just see it pop up all over the place for convenience's sake. And then, yeah, we'll talk about it more in depth in week 7. And what exactly is a collection? Are those like functions? And that's a really good question to ask, for the collections topic here. Collections in general really just talk about, it's sort of like one level up, one layer up from things like, a list or or maybe like a string or a set or a hash map, an iterator, all these kinds of things. Basically, like I have a variable in general lets me store one thing, right? It might be like one animal, one dog, one student, that kind of thing. But, often we want to be able to work with many things, but we're not going to really know in advance how many things there are. Like if I know there's specifically going to be 2 students for some code that I'm writing, I could write student 1 and student 2 as my 2 variables. But as soon as I need to work, let's say write some code to deal with many students in a class where I'm not sure who the students are going to be, how many there are going to be, and so on in advance, I'm going to need to store those students in some kind of collection. Now you might just immediately think to, oh, well, you'd store them in an array or you'd store them in a list or something like that. And that's true. That's probably the data structure you might end up going for. But there's also other kinds of collections. So arrays and lists are certainly kinds of collections. But in the same way, you might end up choosing to store your students in a set instead. Rust's canonical set type being a hash set, which is very similar to it's very similar to a list, but it doesn't actually have any kind of ordering. So a list has the 0th element, the 1st element, the 2nd element, and so on. Whereas a set is just a collection of elements with no particular ordering defined. So it seems like you're giving up something. Like the list seems better, it has ordering, whereas the hash set, you just lose that ordering. What am I getting in exchange? And the answer is it'll have better like performance characteristics in certain scenarios. Like if you spend a lot of time trying to check if something's in a list, well, if it's, if you're checking over a list, you'll have to scan across the whole thing. As the list gets really big, that takes a really long time. Whereas a set, it's approximately constant time. So even as the list gets really massive, it's still extremely, incredibly quick to check if something is in the set or not. And so when we're looking at this topic, we're going to be looking at things like vectors, strings, and hash maps quite a bit. Also this iterator thing, which we'll bring in today as well. But the idea generally is that there's a sort of blanket, like an umbrella term for all these different kinds of data structures that help you deal with many elements together, grouped together. And that's what we, would define collections as, at least in the context of this course. So hopefully that is like a good enough, introduction there to what we really mean when we say, what are we talking about here with collections? Cool. Okay, so I suppose let's kick off again, pretty much where we left off, which is we talked about, there's a whole bunch of collections here available, and there's a few that you're gonna see a lot more than anything else. Vex, string, hash map, really big ones. Hash set, still relatively common as well. But a hash set really ends up just being a specialized hash map. It's just a hash map where you have all the keys and the values are just empty. This is where I said that empty tuple can end up being kind of handy, because base. Oh, am I going to be able to show this? Oh, because it uses hash brown. Hash brown. Oops. Hash brown. There it is. Here we go. Hooray, that's what I was looking for. So a hash set really just wants to use a hash map internally because they really implement basically all the same stuff. A hash map has like keys to values. So you might have like a string goes to a student or something like that. And it gives you this key value data store. Whereas a hash set really kind of like a hash map where you're only using the keys. So it's got all the same, implementation and characteristics, but it's not a key value data store. It's just you have a set of keys. And so this is where this empty tuple that I talked about in week 1 becomes quite handy. A hash set of some type T really just ends up being a hash map of that type T, where the key, the key is a T, the value is an empty tuple. And then all the like methods on this hash set end up just going, call this dot map, call the map implementation of this thing. Like say, if I want to get the capacity, self.map.capacity. And so it can just delegate everything. Check if a hash set's empty, it's whether the map inside is empty, and so on. It ends up just delegating all this work down to the inner hash map with a value type, like key value, with a value type that basically doesn't exist. Empty tuple has no data inside it. It's what we call a zero size type. Anyway, that's just an aside. I just like saw it there and thought might be worth throwing that in. More of like extension content than anything. So if it's blowing past, it's all right. You don't need to worry about that bit so much. Cool. So we talked about vec a bit. We talked about strings. We talked about maps a little bit. I'd like to experiment a little bit with iterators, but we're going to ease into it just by starting off with this longest equal run imperative version over here. Okay, so we're trying to implement another one of these, call it like a collection function, like the find the median, find the mean, these little exercises that we've got for ourselves. And this exercise is called longest equal run. The idea is it takes in two lists, X and Y, which are both just vecs of I32s in this case. So imagine we add list 1, 6991, 1, 2, 3, or something like that. And list 2 might be something like, let's say 1991, 3, 2, 3, something like that. Okay. So this is an example of what X might look like and what Y might look like. And our overall answer should just be a number. And no tricks with this one. We don't need to do an optional or a float. Really just should be a number. And the number is going to be what is the longest equal run. So, okay, there's like longest in here. First of all, what's an equal run? The idea is if we can look between these two, and I'm going to make it a bit bigger actually. We can look between these two lists here and find like columns that match up. See how like this 6 and 1, they don't match up. So they're not an equal, they don't form part of an equal run, they're not equal. But 9 and 9 are equal, and so we start off a run. 9 and 9 are equal, 1 and 1 are equal, 1 and 3 aren't. Okay, so this here is an equal run. And the run needs to be contiguous, meaning it's you can't sort of, okay, say skip this one and then include this one as well. They all need to all be next to each other. So this is an equal run of length 3, right? 3 numbers, 1, 2, 3. And there's actually another equal run in here right there, 2, 3. And this is of length 2. So these are both equal runs. And we're interested in what the length of the longest equal run is. So we have one of length 3. We have another of length 2. The longest is 3. So this, the output should be equal to 3. Okay, that makes sense, like what the goal is here. And we want to implement this for any lists. That includes, for example, empty lists, right? If we got Y, X and Y being empty lists. It also includes if the lists are potentially different lengths. 1, 2, 3, where Y is just 1, for example. So this one here should be an output of 3. That should be an output of 0. And this one here should be an output of 1. Of course, if these were, it's worth noting, if these were different numbers here, like 5, then the output would be 0. There's no equal run at all between the two. Okay. Does this make general sense? Our goal. We want to obviously establish our goal, make sure we're on the same page before we, actually start going off and trying to put something together code-wise. Are sets in other languages also implemented the same way by using a hash map? That's a good question. I'm not 100% sure. I'm sure it would vary from language to language. And it depends on, I would say, the language's capabilities and their, like, let's say, desire for performance characteristics. Like, for example, if we're in the mindset of a programming language designer who an explicit goal of their language is to be very efficient, very, you know, fast to execute and so on, you know, languages like C, C++, Rust, then they're going to make sure, okay, like really high priority goal of this implementation of a hash set is that it needs to be really performant. Now, if their language gives them a way to build it by using a hash map in a way that it doesn't sacrifice performance, then they'll probably do something like that. But if your language doesn't necessarily have the capabilities to do that, like if you don't have a zero size type available to, you know, get rid of that value and not have it affect your runtime performance, you probably like wouldn't be able to do that. You wouldn't be able to have that as a possibility. So it would depend on your language's like goals, the priorities that it has, and also, you know, the functionality, the capabilities of what that language could do, I think is is what comes to mind. And yeah, but if you manage to find out, you know, a blog post on the forum or something like that would be super interesting, to find out. Cool. In any case, let's give this thing a go. So we're certainly going to need to iterate across all these elements. All right, we're going to need to iterate across all of them. And like we need to iterate across them together, right? Like we need to sort of be looking at this one and this one and this one and this one, this one and this one. So I can't just go for, let's call it A in X and then for B in Y and like write my code in here. Because this is going to say for each element in X, look through all the elements in Y. Then the next element of X, look through all the elements in Y and so on. Really, we want to be looking at the elements pairwise, like look at these two, then look at these two, then look at these two. So a natural tool you may sort of reach for as, as a functional programmer might be zip, but we're going to go full imperative on this one. So we're going to start by using some kind of index, something like a let I is equal to 0, right? Now, of course, you know, we're going to do like a for I is 0, I is less than some length, I++, and so on. But the question is, whose length, right? Is it this one's length or that one's length? And so, like, you know, the answer realistically is, well, if we go for the long, like, you know, X's length in this case, then we're going to end up getting like an index out of bounds exception. Like it's going to crash our program when we try and access Y over here and over here. So we really need to be targeting specifically the shorter length. So let shorter length be equal to, so we need to find X's length, we need to find Y's length, and then find the minimum of those two. Fortunately, Rust does have a nice function to make use of. Oops. We can say, I don't know why it did what it did, but in any case, I can fix it up. Something like this. It's going to complain, hey, you're not returning a usize. It's all right. I'm still working on it. So I have my shorter length out of the two there. I could also write this, just as a fun fact, I could also write this as x.len.min of y.len. So I could call that same function like this, you know, if I so preferred. I think it's a little easier to read this way, but that's up to you. Are zero size types unique to Rust? No, not unique to Rust, but certainly not available in every programming language, I would say. Okay, cool. We've got the shorter length. So then we're going to say something like, while I is less than the shorter length, do some stuff, and then I plus equals 1. It's worth noting Rust does not have I++. And the question, you know, that seems pretty simple. Why would I not have I++? And the answer is I++ being used as an expression in many programming languages is extremely confusing. Like let hello be equal to I++ plus I++, right? Or I++ plus I, like this. This would be well formed. And we're going to talk about this a little more when we talk about undefined behavior in, you know, some lecture as it comes up. There's a very interesting story to be told there specifically with I++, so we'll get there. In any case, I plus equals 1 does the same thing at the expense of a couple more characters. Cool. So now we can get these two values. So ask for a and b out of x and y. Right, and so this will be like 6 and 1 or 9 and 9 and so on. That. And we're really interested in if they are the same, if a is equal to b or not. Okay, cool. So then if they are equal versus if they aren't equal, we're going to want to, put some logic in here. If they are equal, we're sort of progressing on a run, right? Like in this case here, equal, 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 it's sort of generating a new run. If they're not equal, then, we're not on a run, and it might also cancel an existing run. So often with these things where we're trying to find the maximum kind of value along the way, you might be tempted to write something like let the current run be equal to 0 and let the longest run be equal to 0. We can write something like if they are equal, then the current run increases. If they are not equal, then the current run is now equal to length 0, right? If they are equal, the run's gotten slightly longer. If it was 0 and they are equal, then it'll start a new run by incrementing 0 to 1. If they're not equal, then whatever run we were currently on is over. Importantly, we need to make sure if the current run is greater than the longest run, then realistically this is now the longest run, isn't it? So if the current run has exceeded our longest recorded run, this is now this is now officially our longest recorded run. At the very end, we'd probably like to give that longest run back, and I think we should start testing this out. Okay. So I've got some test cases that we had over here. So we'll bring this, let's say, this code, if true, return, just so we don't get all this clogging up our terminal. Okay, cool. And let's turn these into some test cases. So we're going to try longest equal run imperative of something like this. Oh no, I do need this one. Okay, cool. 6991 123 and 1991 323, like that. Actually, let's do this. And I have two more test cases. Okay, so this and this. Test 1, 2, 3, and 1 out. And 1, 2, 3, and 5, like this. Okay, these are all our test cases. So we're expecting 3, 0, 1, 0. Okay, materials. Okay, yeah, right here. 3, 0, 1, 0. Is that correct? 3, 0, 1, 0. Yep, seems right. And so here is an imperative solution. Pats on my own back, like I did it, yes. But of course, this is really just like step one. We have a little bit more exploration to do than playing around the hat. But before we move on to approaching this problem with a different perspective, I want to check if there's any questions about anything we did here so far. Or potentially, are there any improvements or weak spots? Things that you, okay. So basically, what I'm asking is, is there anything you don't quite understand that you want to clarify? Is there anything you like about this solution? Is there anything you don't really like about this solution? This is really like the crux of what this course is about, where this at the end of the day is code. The code does the right thing. So as far as the machine is concerned, this is just working code. If we change like variable names around the place, if we change the way we call functions slightly, the machine doesn't care, right? It's gonna still execute the code. This course is about us humans looking at this code and going, what do I like about this? What don't I like about this? Can we use for I and 0 up to shorter length? Yeah, we absolutely can. So we have like let mut I is 0, I plus equals 1 down the bottom here. We could certainly change this to for I in 0 up to the shorter length. Does it still work? The answer is 3, 0, 1, 0. Yes, it still works. Do we like this better? Is this like, you know, do we think this is an improvement? And if we think it's an improvement, why? If we think this is a downgrade, like it's not as clear as the previous solution, or, you know, trades off some other thing, you know, why don't we like that? Do they have a way? Do they have to match up pairwise? Like, what if one starts at index 3 and the other starts at index 5? So yeah, that's a very reasonable question. We're going to say within the constraints of this problem for the longest equal run, they do need to sort of be in the same position. You know, you can imagine index-wise, like the same position in their respective lists. But that would also be a very interesting problem to solve as well. If you can imagine these lists sort of being like shifted across from each other. Like if it was like, these are the actual lists, but we sort of compared them together like this and found a better run that way. That'd be a really interesting problem in its own right. Okay, so yes, before it would have been possible to forget incrementing I. Also, the logic is grouped together nicely, so it's immediately obvious what I is for. Those are some really interesting points. And I'd like to, here we go, really like come back to this one and illustrate what you're saying, you know, on the big screen. So before up here, what we're saying is we have I is declared up here. We then like make use of it down here and down here. See how the logic around this I variable is spread all the way around the place. Now, of course, this could be moved right down there. That's a suggestion that someone could make. You'd, you know, make, if you're doing like a pull request review, someone's doing a code review on what you've written, they might leave like a nitpick. Often this is the thing that comes up in code reviews. Nitpick, like move this variable declaration down to the loop, right? And so maybe like it was up here. Oh yeah, that's a better spot for it. I'm going to move it over here. And so that could get picked up, but there's really no doing that with this down here, is there? Right? Like I plus equals 1 needs to be at the very end of the loop. Like you could in theory put it over here, but is that actually really going to be any better for someone trying to read your code? You know, I'd wager maybe not. And this is absolutely forgettable. If I happen to forget that and run my code, that's what I get, right? Just an infinite loop, and my computer's fan starts to ramp up because it's working really hard on this. So yeah, absolutely. This is an interesting comparison here to say, I've lost the like undo history. That's fine. You know, is there something to be had for saying for I in 0 up to that shorter length? Maybe this is something you prefer. Maybe you find this less clear. All right, but something to consider. Let's see. Don't need to worry about updating a variable, so I feel like the for loops are more lazy-friendly solution. Yeah, and I think it's a, what is it? It's like a Bill Gates quote. I think it's Bill Gates who said something like, he likes to hire lazy software engineers. Bill Gates, lazy software engineers. Here we go. Yeah, there's a very famous quote from Bill Jobs. I choose a lazy person to do a hard job because a lazy person will find an easy way to do it. So I would say on average, like, and this is, I'm sort of being like a little bit jokey here. It's not in the exact sense that I say it, but like software engineers are on the lazy side. If there is an easier way to achieve a task they're trying to do, they'll often find and end up going for that easier way. So trying to optimize for that is actually an interesting way to approach the problem. Sometimes I forget to include the I plus equals 1 in while loops, so I prefer it in, yeah, exactly. Could we use iterators for both vecs? That's a really good question, and we're certainly going to get to that in just a second. I really like that idea. You don't even need the I variable though, don't you? Yeah, so in this imperative approach where we're trying to, you know, index them column-wise together, I think we probably do need this I variable to, you know, index them against each other, make sure we're looking at the same element on each list. But there's certainly other approaches, other styles of programming where maybe this index doesn't make an appearance at all, which is probably what you're alluding to, I imagine. And so, yeah, we've had a little bit of discussion about this kind of approach. I'm going to write something that tries to achieve the same thing. Oh, more that you don't need the let mute I. Exactly, that's totally right. So when we write this, we don't need to write let mute I at all. So it sort of saved us an extra couple lines of code, you know, if that's your measurement. Now this is, I would say, I'll bring this down here. That is just a genuine improvement to the imperative approach, I'd say. This kind of loop, I would say, is very typical of imperative code. You know, if we're writing C, which is really quite a relatively imperative language, we wouldn't be able to say for I in, you know, this range of numbers. That's sort of starting to teeter on the functional side. So I'm going to revert the code here. When we come back to the mixed approach, maybe we might end up revisiting that. We'll have a look. But that's I really do like that suggestion, and it's really interesting to explore. Okay, so let me set up these test cases again, just so they're ready to go. But I'm going to do this for the functional version instead over here. So just to make sure they're, once I finish implementing this, it's going to be doing the right thing. Now, I'm going to write a bunch of code. You're going to sort of watch it appear, and you're going to be confused about a lot of different bits and pieces. And I'm going to go through some bits more than others, but I'm going to sort of try and write this out first. Okay, so let's start with X intuiter, and I'm going to, actually I'm going to write this here, zip that with y.intuiter. Zip is something that was actually mentioned in the live chat a little earlier. I'm going to map A and B over to A being equal to B. And then I'm going to fold this. I'm going to fold this across 0, 0. And I'm going to have a function that takes in, I always forget the ordering of this, so I'm going to double check. It takes in here, B, and then the item. Okay, cool. So we'll see this in a second. We're going to call this current longest, and then our item being eq, call that. If eq else, I'm going to say if eq, then longest is equal, let's say let current equal current plus 1. Let longest be equal to usize max of current longest, and give back current longest. Over here, I'm going to say the current is equal to 0 now, and the longest is what it is. Okay, then over here, we're going to say dot, we're looking for the longest, like that. Okay. If I run this, we'll see 3, 0, 1, 0. 3, 0, 1, 0. Okay. Now you might have watched this and gone, oh yep, Intuit, zip, yeah, map, okay, a fold, yeah, okay, cool. Follow along with this, some weirdisms and like a dot one, and been like, oh, okay, but I got what you meant. That's probably the slim minority of viewers, and I'm imagining the vast majority looked at this and went, what the hell is he typing? What is going on? Like, I'm losing my mind. And it just ended up working at the end, and like, that's just, I don't even know why. Okay, so what's going on here? And why do I expect that some students would have been able to, you know, reasonably follow on with the gist of what was going on, whereas some students would have no idea? And the answer is that this is quite a functional approach, right? This being quite imperative, this being quite functional. The important distinction, I think the most succinct way to describe the difference between imperative and functional approaches to programming is this is the way I've heard it being put, and I really quite like it. Is that when you're writing like imperative code, you're really like explaining how to do your task. This is, you know, you're telling the computer this is how to do the thing. Functional code, and it's so convenient that imperative and functional end up being the same number of characters, isn't it? You're really describing how to do your task, or not even necessarily, well, yeah, in a certain sense, describing how to do your task. Now these seem kind of similar, but over here we're saying, you know, set like a number to be 0, 0, this number 0, then, you know, do this loop, pull this thing, check if they're the same, increment this number, if, you know, do the thing, whatever, add 1 to this variable, continue onwards, so on, right? It's like there's tools that we're making use of here, but they're relatively bare bones tools. And we're really sort of explaining how you would do each step of solving this solution really to the computer, to the, you know, to the compiler, using that programming language. Whereas functional code, you're more trying to describe what this task really is, right? How to like break this task up into different pieces, like a zip, a map, and a fold. And there's less overall logic going on because the logic ends up being performed generally by these, you know, these functional, you know, functional idioms, functional tools, zip, map, fold. Now, you know, Rust, these are clearly implemented in Rust. If you go to the standard library docs and you search for zip and map and fold and so on, you'll find them here, but they're not unique to Rust. Again, it's that Rust is not a new language kind of take here, where, and again, this is why I think some students would have been able to vaguely follow along, where zip, map, and fold exist in many programming languages. And these are like common words and procedures, you know, across programming as a whole. So it ends up being quite convenient in that, you know, like Rust, we need to learn the syntax for sure, and for like either of these approaches. And there's a lot of syntax going on here for each of these different operations, and, you know, the tool we're using specific to Rust. You know, kind of specific in the same sense. A while loop is you know, a pretty general concept. Declaring a variable is a pretty general concept, and so on. But although this may look foreign to a lot of, you know, to a lot of you watching this, once you learn functional programming, this won't look, you know, this will look approximately the same as what this looks like in a relatively unfamiliar language. So something that I just want to sort of, yeah, get off the bat there. But yeah, there's a lot less explaining like how to do things. So notice there's no index at all. There's no index at all with this functional approach. This 0, 0 here is representing the longest run, the current run. So those still exist in this case. But there's no like 0 plus equals 1 or for I and up to. That's being dealt with by this zip thing. So let me try and explain what the data looks like at each step here. We start by turning X and Y into iterators. Excuse me, sorry. Turning them into iterators. Now, iterator is really Rust's like gateway into functional programming for collections. Oh, look, it's right here. Iterator is really quite convenient in that it's what we call a trait. We're going to talk about traits and get into even deeper into the iterator trait itself in week 5. Week 5 is when we get into that. But the idea generally is you can implement iterator for any type that you'd like. It's certainly implemented for vec, which we're making use of here. Technically not. There's like something called into iterator, and anyway, we'll get there. But you can imagine for now, it is. Just accept my lies, I promise. I'm just trying to get to this thing here, this one, and then bear with me. Down here, here. Oh no, don't do that. Show me your implementation. Why is it not showing me? Oh, this is, oh, I clicked the wrong thing. My mistake, sorry. Here. Where am I? I'm still in here. Sorry, I've gotten lost. Just give me a second. Right, this one. No. I can do this. This one. There it is. Sorry, there's a lot of like the same. I've got lecture brain on, so I'm instantly a little bit dumber. Okay, here we go. This is what I was looking for. Okay, this looks a little bit crazy, so just bear with me. The idea is that I can say implement iterator for any type. Let's just imagine this says vec here. The implement iterator for a vec of some type t, to get the A. All you need to do is define two things. What type of items your iterator produces. So a vec holds many t's within it, right? So a vec of string holds many strings. So the item that there's many of in a vec is a t. Imagine again like a string. Vec of string, the item is a string. So you define this. That's a really easy line to write. Type item is t, and then you implement one other method called next. Next says when someone asks for the next item, optionally give that item back. And it's optional because we want like the next item. Say it's a vec of 1, 2, 3, like they have over here. When they iterate across it, next should give us 1, then 2, then 3, and then nothing, right? That's the end of the iteration. So that's why we have an option. It's going to keep producing some 1, some 2, some 3 until it runs out of items and then starts giving none. So you need to define the type of item and this next function. You just need to tell me how to get the next thing out. And if you know C++, you might recognize start pointer, end pointer. This is zero size type, so you can ignore all of this. But basically, it's just saying, you know, like add 1 to the pointer, like move the pointer along to the next element and read the value at the pointer. You know, that gets me the next thing. And then once we reach the end of the vec, start giving back nuns. You know, this is all crazy Rust code. We're not expecting to understand this. But the idea is what you have to implement in terms of iterator is very simple. What item do I give out? How do I, and then like tell me how to get the next one. Now, here's like the big reveal. When you implement literally just this and this, that's it. That's all you need to write. You get all of this for free. See all these methods here on the left-hand side? Those are all implemented just in terms of next. All these, and so like if I scroll through the actual like documentation here, it goes on and on and on and on and on, right? That's all capabilities of iterators. So our old friends like zip over here, or map up here, or fold, and so on. Those are all just implemented for all iterators. And so vec, you know, any collection type really just needs to implement that iterator trait, those two little things, and it gets all this for free. It also means that all the collections have a common language for talking to each other, right? Like a vec can cooperate with an array, can cooperate with, a set, can cooperate with a hash map, can cooperate with, and so on. Because they have this common language they all speak, which is, you know, iterator. They can all be turned into iterators, and iterators are great at working with iterators. So we can start looking at what these iterator functions tend to do. So zip zips up two iterators into a single iterator of pairs. So you can imagine I have a pair of lists, right? I have a pair of lists like we see here. And imagine I'd like to turn that into a list of pairs like this. 9, 1, 1, 1, 3, 2, 2, oops, 3, 3, like this, right? So we have a pair of lists, turn that into a list of pairs, where again, it's just looking column-wise, 6, 1, 9, 9, 9, 9, 1, 1, 1, 3, so on, right? This is really the first step of our problem, right? That was the whole I equals 0, I is less than shorter length, I plus equals 1, let A equals x of I, let B equals x of y of I. All that stuff is zip. And the reason that this exists is because this kind of idea of looking at two lists, column-wise, looking at their common things, is common, right? This is something that happens across many different problems. And so when we're writing our imperative code, we often have to re-implement, we like to often talk about this as reinventing the wheel. Like every time we need to look at two lists together, we end up needing to write the same code. I is 0, I is less than this, x of y of I plus equals 1, so on, right? And especially this shorter length as well. This shorter length is built into zip. How do I know that? It says if either iterator returns none, next from the zipped iterator will return none. So if one iterator runs out, then zip itself will run out. The cool thing, of course, is that when we zip together one iterator with another one, right, a pair of iterators into an iterator of pairs, we actually get an iterator back. You see it gives back this zip type over here. And if we look at zip, you'll see it implements iterator itself. And the items it produces are whatever A's item is, A item, and whatever B's item is as a tuple, as a pair, right? So it's itself not special. It really is just an iterator as well. But the items it produces is now a tuple of those two, a pair of, each of their items. And I'm hoping this I haven't checked on, but zip import. So this is the thing that's kind of a bit tricky with, when you're trying to educate based on the standard library, is I want to show you, like, it's probably a relatively simple implementation, but sometimes it can be a bit of a pain to, like, because they're using macros and stuff like that. Yeah, this is the code that it ends up being. It just ends up being a bit tricky to find. It just says get the next thing out of A, get the next thing out of B, and then give back those elements as a tuple. That's its next implementation for iterator. There's also these question marks going on, which says if either of these things fail, just give back none from this whole function. We're going to look at the question mark iterator, the very last thing we do today. And so, yeah, you write this code once. This code being the equivalent of this, and this all together. Someone wrote this code somewhere once. They've tested the hell out of it, make sure that it works in all scenarios, and then you just make use of that. Now we don't have the same problem where I forgot, like I accidentally set I to be equal to 1, or I accidentally did less than or equal to over here, or I like missed the I++ and that kind of thing, right? All those things you would tend to have to unit test your function for, make sure that you haven't made any of those slip-ups along the way, right? That's already been tested the hell out of with this zip function. Of course, logic errors are always still in scope here, where you could have just, solved the wrong problem, essentially. But it's certainly reducing a certain class of errors. Now, there is, of course, a trade-off. This, to an unfamiliar reader, is probably easier to understand, like going from zero understanding to total understanding, probably quicker than someone who's unfamiliar with this functional code. And now, even people who are quite familiar with functional code might be perfectly happy with zip, might be perfectly happy with map, but then they see a fold like this and they go, this is just getting silly. And me personally, this is personal opinion alert, not course prescribed, you'd need to, again, agree with this or anything. I find this to be a little egregious. This I wouldn't like to write this kind of code myself or maintain this kind of code myself, because it is generally just a bit difficult to understand. But I'm personally quite happy with the zip and quite happy with the map. So I've talked about the zip. The zip lets us go from, again, this kind of view of our input data into the pairs that we really care about. And then map, what map allows us to do is it says, take each element that our iterator is producing and turn that into something else. And that's what a mapping function is. So map this thing to be something else. And what I'm mapping it into is, I've run out of letters, I guess. So Z will just go to like W, whatever. I'm mapping this into each element. I take, this is what's called a closure syntax, lambda syntax in Rust. If you just sort of have to look at it and, just experiment around with it, and we'll look more at closures properly in week 7. But I'm basically saying between the bars, between these vertical bars here, it's saying this is the input, and then after the vertical bars is the output. And so the input, I could just say like, I could just call this like input here, and then say input dot 0 is equal to input dot 1. There's actually a little trick here. If you have a tuple of elements, you can see, oh sorry, I wrote 2 here. If you have a tuple of elements, you can get the first element with dot 0 and the second element with dot 1 and dot 2, dot 3, so on. People generally, I think people quite hate the dot number syntax at first. So I'm using a pattern here. We talked about patterns yesterday to destructure this into A, B, and then just checking is A here equal to B. So what I'm mapping this into is these are different, so false. These are the same, so true. These are the same, so true. These are the same, so true. These are the same, different, so false. True, true. I've effectively changed my problem from this, input data. I've transformed that data into false, true, true, false, true, true. False, true, 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 false, true, true. And now the problem has been simplified. All I have to do is find, like, what's the longest run of trues. So I'm sort of, just mutating the data. I'm not actually mutating it, but sort of changing this format of data step by step, reducing it into a smaller and smaller problem until I'd like to tackle it and reduce it or fold it down into my solution. And this here ends up looking basically like, the problem scope that's going on here, but in a fold, which I'm not going to get into the details of fold, because we'll be here all day. But this is a different approach to what we're at here. And so I don't know when that message popped up, the pipe in the map function means, but just to quickly recap that again, we have the pipes here. Between the pipes is our input, and after the pipes is our output. So each element we take in A and B, right? So like, because we have an iterator over tuples, over like pairs, and then just spit out, the Boolean, the question, true or false, whether the first element is equal to the second element. And now this gives us an iterator where the items are just Booleans. And so now from this point onwards, we just have to solve the problem for where where we're just working with Booleans. So this here, we have an iterator where the item is a tuple of the elements from each list, like that. Maybe I'll make them line up like this. Right, so that's sort of what's going on here. In any case, we won't go too deep into it now, but it's worth noting that Rust really really supports both approaches, right? Like this works and does the right thing. This works and does the right thing. The good news is you can generally mix these approaches as well where you see fit, where you think you're going to get the best of both worlds. This is exactly what you're saying here with fold seems excessive. Can't we just use for each or another for? And the answer is yes. Let's give that a go. So imagine we'd prefer to write it something like this. Let mute current run be equal to 0 and the longest run is equal to 0, right? An imperative approach, but maybe this made more sense to us. At the very end, we're going to give back whatever the longest run is. Now we could say for, and let's say like AB in x dot into iter zipped with y dot into iter, like this, right? Go back up to our imperative code and steal some of the bits in the middle, right? And this here is another solution that sort of sits somewhere in the middle. The iterators are maybe like quite useful to take advantage of zip. Maybe you also, would like to reduce this from being A and B into just like for like, matches in this. Just check if they match and add in like a map here, that we had from this thing over here. AB goes to A equals B, and this would work as well. And so you've got to like, there's going to be a line in the sand that you draw and you say, this is the kind of approach I'd like, this is the kind of approach I'd like, or where do I draw the line sort of in the middle? But I imagine if I go and grab this code over here again, and I go change this to mixed, like that. I'm hoping if I haven't screwed anything up, we probably get the same results. 3010, 3010, 30 over here, 10. Yeah, so it's doing the same thing. And the question is, which one do you think is going to be the best for you? And by you, of course, I mean like whoever this code is really important for. Often that's, the engineers writing it, the engineers maintaining it, but also, the business that it's for, assuming it's for a business, or, your users as well, what's going to be the best approach. And it's going to change. It's going to change in different circumstances, which is why this course is all about, playing around with this, trying different approaches, and trying to build up a almost an intuition for how you reason about how you would approach, solving problems with code. Are there any notable performance differences between functional and imperative approaches, and what does fold do? So fold, I'm gonna just leave that as like a bit of a black box. I'll publish this code as I always do after the lecture, and you can poke around at it as much as you'd like. You can read in the standard library source code, if I've lost it, about how they describe folds, and you can see it's a relatively long description here, and you can look up elsewhere, like functional programming fold, just on Google. If that doesn't end up being super helpful, feel free to also ask on the course forum, and I'm happy to write like a long form explanation that goes into this. But we'll basically leave it at that. It's a little bit of, functional programming black magic. It's one of the more difficult, primitive operations to understand. Now, so that other comment, I really like that one. Are there any notable performance differences between functional and imperative approaches? And the answer is, it depends. And usually the it depends is based on your mostly your programming language, and especially your programming language's philosophy. In particular, there is a relevant philosophy here called zero cost abstractions, which was the term itself, I believe, was coined by Bjørn Strostrup, who is the inventor of C++. And this is something that certainly C++ subscribes to, certainly Rust subscribes to, and some other languages. But the idea is that these programming languages provide abstractions. Things like structs are an abstraction, functions are an abstraction, a very simple one, albeit, if, for, while, these are all abstractions, but they get more complicated. Things like iterator is also an abstraction, and all kinds of other, types and utilities that the language provides. And these languages that subscribe to this philosophy aim for those abstractions to be zero cost, and zero cost in two senses. So zero cost meaning, one, if you don't use it, you don't pay for it, for some like definition of pay, right? So if you don't use iterators, then iterators shouldn't cause any kind of performance difference for you. So the language shouldn't be slower or worse performing as a whole just by including iterators that you end up never using. So if you don't use it, the language should be as good as if it didn't include that feature at all. And if you do use it, it should be as fast, or let's say like performant, as handwritten code. And I write performant here, the main thing you're interested in is how fast does your code run, but also there's other metrics, things like memory usage as well, is an important metric for, these kinds of languages, C, C++, Rust, languages that have a lot of emphasis on things like zero cost abstractions. So basically, if you do choose to use iterators, it should be as performant as if you wrote everything yourself. And by writing everything yourself, we really mean this over here. So this should be the same performance as this, which should be the same performance as this. And I bet if you take each of these and you do a like cargo build, importantly, very importantly, release, right? A release build, meaning like zero cost abstractions do not hold for debug development builds. No one cares about whether the iterator is faster or slower on a development build. We care about it specifically for a production release build. If you looked at the assembly code generated for each of these versions, they're going to be extremely close, potentially even identical between the three. Sometimes you even find that the higher level, for some definition of high level, functional approaches sometimes end up being faster due to having more static knowledge that the compiler can reason about. But in general, we're looking at these usually end up at the same, performance level. So it's an interesting philosophy, and it's important to, especially when you often end up committing to a programming language, in the sense that we're starting a new project, we're going to need to write code, we need to choose a language for that. You can't just write language agnostic code. You can't write pseudocode to build a website, really. So you're going to need to choose a programming language. And generally, if once you choose that programming language, you're going to have a commitment factor to it. Now, of course, that's not to say that you couldn't migrate away from a programming language, but it's going to take some amount of effort. And generally, as your project increases in size and increases in other dependencies relying on it, or you depend on more things that are, say, language specific, the more friction it's going to be, the harder moving away is going to be. So you really end up often making commitments to certain programming languages. My suggestion is make sure you keenly understand your programming language's philosophies, their guiding principles, because you're not just committing to the programming language as it is now, you're often committing to what it's going to be as long as your project lives. What is Rust, C, C++, Java, Go, Python? What are they now? What are they going to be next year, in 5 years, in 10 years, in 20 years? If your project certainly lives so long. So it's something to keep in mind and make sure that you have a good understanding of, before making that commitment. Okay, let's take a break. That's basically the end of the collection stuff I wanted to talk about over here. So let's take a break until 10 past. I know it's a little bit of a shorter break, but let's do that. Type some questions in if you have them in the break, and I'll see you back at 10 past. Okay, all right. So let's get back into it, and we're gonna we'll have 45 minutes to spend on this other topic here, error handling. So when our code doesn't take the happy path. And just in case you want to start playing around with any of what we just wrote, I'm gonna let go 3 longest equal run. I'm gonna push that up now, just so you're immediately able to start playing around with that if that's what you'd like to do. Okay, we've got some code to play around with here, and we're gonna start off by looking at some C code. All right, includes.ioh int main void. Open a file, hello.txt in read mode, trying to read the file. I'm going to allocate some memory, some characters for a line, and say f gets 1 line, with the size of that line from this file. Print that line out. Okay. Now my question is, and this is a question for everyone here in the chat, what could go wrong? What could go wrong here? What's maybe not being dealt with? What are some dangers? What could go wrong? What if the file doesn't exist? Yeah, that could certainly go wrong. What if the file doesn't exist? So, let go 4 over here. I have got a hello.txt. If I clang this errors program and run it, cool. The file does exist. What if it doesn't? Instead of removing, I'll move it to hello.txt.old. Segmentation fault, core dumped. Okay, sweet. Reading more than the buffer size. Yeah, what if that line is really, really long? So I'll move this back to hello.txt. What if that line is really, really, really long? I'm guessing that ought to be long enough. 1056. Okay, that's going to be long enough. If I put like hello here at the very end, right? And then run it. Just going to truncate the data. We don't get that hello exclamation points at the very end. So that could go wrong. We don't close the file, right? What about like fclose that file down the bottom here? That didn't happen. How do I know I have to do that? What if I can't like open or read the file, like I say, if I don't have permissions to read? Yeah, for sure. So if I have, if I chmod this hello.txt, 000 hello.txt over here, I don't have permissions to read from it. What's going to happen now? Segmentation fault core dumps. Yeah, all these are things that could certainly go wrong. Okay, so extension of this question, I'm going to bring it back to 644 hello.txt. Okay, it's working again. And maybe we'll even change this back to just hello world for now. Okay, it's great. Okay, so we know that there's a bunch of things that could go wrong. But guess what? My code compiles. My code compiles without warnings. If I have -w all, like turn on all the warnings, it compiles without any warnings. If I have -w pedantic, don't just turn on all the warnings. Turn on all the warnings that you don't even turn on by default because they'd just be too nitpicky, too pedantic. Compiles without warnings, right? So my question is, how did you all know this? Right? How did you all know that fopen, let's see, like what could go wrong? Fopen, the file doesn't exist, or that I might not be able to open or read the file? Or is there even more things that could go wrong that we don't know about? Like, what if we don't have a file system at all? You can run C code in a system that doesn't have a file system at all. What would happen then? And then, knowing that we might read more than the buffer size, and what's going to happen there, right? How did we know that that's something that could go wrong that we might need to deal with? Closing the file, right? Something that we're generally meant to do here. Fclose file at the end. How do we know we had to do that? Right? Like, how do we know all this? And so we have, unfortunately, experience sad face. Yeah. Is there any way we could have known this without experience? Like without having run into this previously, is there any way that we could have known that these things, might happen ahead of time? Documentation, the man page. Yeah, for sure. If I go to manfopen, actually let me put it in the big terminal. Manfopen. Zoom it out a little bit. We'll probably find errors over here. So we could get e-inval. The mode provided to fopen, fodopen, or freeopen was invalid. So that's something we maybe didn't think about. What else could go wrong here? What if oops, not that one. Oh, not that one either. What if this is not valid? R is not a valid argument. Is something we have to think about as well. Excuse me. I've lost it. Errors over here. These functions may also fail and set error number for any of the reasons specified for the routine malloc. The fopen function may also fail and set error number for any of the errors specified for the routine open. Okay, so our man page has given us homework, basically. It said, okay, the mode might be invalid. You're going to have to go figure out what a valid mode is. Also, any way malloc can fail, I might fail. Any way open can fail, I might fail. You have to go figure out what those are. And so I go up to the mode documentation. I see the argument mode, it needs to begin with one of the following sequences, possibly followed by an additional character. So R plus W, W plus A plus. It can also include the letter B and blah, 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 right? I need to go to man malloc and have a look at errors that could go wrong here. Enomem, if I run out of memory. I also need to go to open, not XTG open. I need to go to this open down here and see what might go wrong over here. Errors. There we go. E-access, E-access, E-busy, E-quote, E-exist, E-fault, E-fbig, E-inter, E-inval, right? And it sort of goes on. There's a lot of things that can go wrong, it turns out. So, okay. We have an idea of what might go wrong with fopen then, but we had to check the documentation. The compiler didn't warn us in this case. The compiler didn't really hint to us that this might be fallible. And this again kind of comes back to the point that pointers have implicit nullability in C. Whenever I have a pointer, it's sort of my responsibility to go, this pointer might be null. I better go check and find out what are the cases where it might be null, where something's in theory gone wrong. And even if it was just a file, you could imagine that the file struct itself has some internal representation of, it not being in a correct state. And so that, we'd have to chase it down. Now, this clearly works to an extent. You read the documentation, you know what you're doing. You are the gifted smart programmer who can, who can manage all of this. Given this is the case for C, and massive, brilliant things have been successfully built in C. Linux, right? Linux is a very reasonable example, is built, well, until recently, basically entirely in C. Now in C with some Rust as well. But, this can work. But is it really, the best case scenario? Is there ways that this could be improved? Now, let's look at, let's think about some different approaches we have here. So there's this sentinel values idea, being that, to check if this went wrong, we need to look out for some kind of sentinel value. In this case, the sentinel value being null here, representing that something went wrong. Fgets also returns a pointer, which we can check if that's equal to null. And then, we're going to be relying on some documentation for some other things and stuff like that. There's also this sentinel value errno, like that, which actually, I'll need to hash include errno.h, error number. And this number, this, might actually give me a hint. E access, we saw that before, or whether it's E no mem, it can give us an idea of what potentially went wrong, and this is its own sentinel value as well, this error number. And so this is a potential error handling, like a, like error handling approach, commonly seen in languages like C, especially language, Pascal we have here, but Go as well. Like, it's not just C and Pascal are quite old languages. Go is relatively, young. Not as young as some others, but still a comparatively young language. But in its philosophy, it really values having a very simple code in terms of being able to understand the surface area of the language very quickly. So Go is often hailed as a language that's extremely quickly to pick up, to be able to learn and write, real code, be productive in it quite quickly. But there's a trade-off with that, at least, in my opinion here. The trade-off being that a lot of the logic of how you ought to write code in a language like C or Go ends up being delegated back to the programmer. The programmer has to have more understanding going on and more context floating around in their brain to be able to write the code effectively, especially when it comes to writing robust code, right? Code that's going to work correctly. Now, also the language design made it easy to not consider the cases where things go wrong, whereas in Rust you get a result when you open the file which already suggests it may not have failed. Yeah, exactly. So, and that's absolutely right. So C here is, it's a language where it's very easy to sort of cover your eyes. And that's a good thing in certain cases. Sometimes you really do just want to cover your eyes, and, I know that things aren't going to go wrong on average, and when things do go wrong, it's really not a big deal at all. I can fix it very quickly and there's no fallout. Perfect scenarios being things like when you're prototyping, or when you're writing, say, like an internal tool that you're planning to use, or just, some employees are planning to use. It's fine if things go wrong. It's all right. Like, we are engineers. We know how to debug things. We'll fix it. That's cool. But, that's not going to be the, your ideal in all contexts. That's why, again, I said at the beginning of this course, we don't want to just hail one programming style, one programming language, one set of tools as this is the holy grail of programming. This is how you have to do it. There's infinite different contexts that we might operate in, each with their own priorities and competing, trade-offs that we need to consider. And we're trying to get you to put yourself in the mindset of all these different contexts, to experiment with a whole bunch of different styles and hopefully get a feel for what is, the right kind of approach and when. Okay, cool. So what have we got? We've got half an hour left. I want to tackle an approach that we see more commonly in a whole bunch of other languages, specifically this idea of exceptions. There's actually two flavors of two flavors of exceptions, as far as I see it: checked exceptions and unchecked exceptions. You can see unchecked exceptions. I have the whole shopping list of programming languages here. This list just like goes on and on and on and on. Really, really common pattern. Specifically, if you've seen like try catch or try except, anything that sort of resembles something like that, you're probably looking at unchecked exceptions or exceptions in general. Java also has this additional idea called checked exceptions, which I think are really interesting because they actually kind of, in my opinion, sit in the middle of unchecked exceptions and this last approach here called sum types, which we'll look at with respect to Rust. So I'd really like to spend some time looking at some Java code and exploring why Java really was the only language that took up this checked exceptions route, why they didn't get so popular, why people kind of didn't like them, and maybe see if we can extract the good parts out of this into, a slightly different system. Okay, so a different way of dealing with things going wrong, with errors. And we're going to, if you're writing Java code, generally you want to use an IDE. It's a slightly difficult language to write in otherwise sometimes. So I've got this IntelliJ set up here, and you'll see the code doesn't compile. Oh my gosh, you're so unprepared. No, turns out it's actually something that I'm going for here. So now I was hoping I'd be able to zoom it pretty easily. That I maybe I'm getting a bit too cocky because anyway, I think this text is probably is probably zoomed in enough to be able to understand. Although I'm gonna see if I can really quickly just try and increase the size a little bit for everyone. Sure. Just up the size, please. 18. Bit bigger. It's not changing the code. No. Go back. This one, editor, general, appearance. This is terrible. This is the worst. There we go. Found it. 20. Apply. Okay, there we go. Zach versus IntelliJ. I win. Okay, there we go. That's a more appropriate size. So I've got some main code over here. Here's what it does. What it's trying to do is it has a list of file names really, and I want to get the first line of each file. Kind of like the C code, which got the first line of hello.txt, but I want to be able to do it with a list of files. So I create a new array list of strings from my first lines, and then I have this list of my file names. For each of the file names, I say grab the first line of it by calling this first line of file function I've defined down here. Take that first line and add it to my first lines list up the top. At the very end, I'd like to print out the first lines. Okay, so this is all relatively simple. This is the one that's actually going to be doing the file stuff. You see it takes in a file name, and it says create a new file like a fopen in C. Then we have this new buffered reader, file reader, just Javaisms, like don't worry so much about this line here. Read one line from the file, return the line back. Cool. So that's what's going on with this Java code, but you'll see that it doesn't build at the moment. It doesn't actually compile. And the reason is due to this line here. Let me get rid of this little section. You'll see that I get these errors cropping up. Unhandled exception, file not found exception, and over here, unhandled exception, IO exception. This is what we call a checked exception. So the idea is, if I look at this thing here, it says when I'm creating a new file reader, when I'm trying to, start reading from a file, this might cause an error. And the way it says it might cause an error is with this actual syntax, code typed in Java throws file not found exception. When you execute this, when you say new file reader, give me a new file reader, you need to explicitly deal with that exception, either with what's called a try catch block, or by saying that your function might throw that. So what I mean is you could write try catch, and then what's the exception here? A file not found exception, like this. So I could say try to do this. If this code ends up throwing a file not found exception, then enter this block here instead. And in this block, we might, do some code that handles that error and then proceeds some alternative way. But you'll see now down here, this code won't work. The fact that I'm trying to now access this reader inside, it doesn't work anymore because sure, it may have been created, it may have worked successfully, but this line might have failed, ended up in the catch block, and so the reader might not be there. So, scoping rules come into play here. And so I'd probably end up putting this code inside here as well. Now we see, this might fail for a different reason, this IO exception. So I need to say, catch a file not found exception, or like an IO exception, this kind of thing. Now it turns out that file not found exception, Java has this idea of inheritance. It's a kind of IO exception. So we really just need the IO exception here, catch any kind of input output exception that might have happened, blah, blah, blah. But now we get a new error, which says, hey, if you try and you return something here, that's great. But if I catch an error, you do this, what string am I going to return? You need to deal with that explicitly. So return like an empty string or something like that. So there's this idea of try catch. This is common to all exceptions. But there's also this distinction I've talked about between checked exceptions and unchecked exceptions. The difference being whether the type system knows about this exception statically. That is, when I say new file reader, it explicitly says here, this throws a file not found exception. And if we look at this, it eventually extends this exception class in Java. It's a type of exception here meaning basically checked exception. But some other things that might go wrong, let's say like if I have a null object, so let's say like string x equals null, and then I say x dot get me like the length of this null string, right? This is going to cause an issue. It's going to cause a null pointer exception, is what Java calls it, right? When you try and do something on a null object. But I don't need a try catch for this. You'll see there's a warning here, but it's not an error. And the reason is, oh no, that's not going to get me there where I want to. The reason is if I look at a null pointer exception, it's this kind of runtime exception, meaning something that might go wrong at runtime, you can try catch for it if you'd like to. So I can say try, oopsies, catch null pointer exception and handle it down here. But the compiler is not going to warn me, right? The compiler is not going to go, hey, check for that. And the reason it's not going to do that is because it would give me this error everywhere. Like all the places where it can't 100% be sure that this thing is not null, it'll be like you need to try catch for a null pointer exception. It would get really annoying. That's why Java said, okay, some exceptions will be checked exceptions, some will be unchecked exceptions. But it's interesting that like, you'd imagine, well, we want to make things checked exceptions where it's reasonable to do that. So then like we know, the compiler is going to say, hey, you need to deal with this thing potentially going wrong, ahead of time before you're actually building your code. But it turns out that they can be kind of a hassle. And I'll show why in a second here. So let's go back to before the try catch over here. And we just had this. Now I said we can explicitly deal with this error using a try catch block in Java, but I can also say, well, things could go wrong inside here. So instead of dealing with them in my function, I'm just going to say that my function as a whole could fail. And so in the same way that this thing here says it might throw a file not found exception, or how this function here says it might throw an IO exception, I can also say my function might throw an IO exception. So my function, if it goes well, it's just going to continue through to the end. But if one of these operations here or here fail, they'll throw their exception into me. I'm going to throw my exception up into whoever called me. In this case, that's up to main here. See how now the error exists in main. This function might go wrong. You need to deal with it. Cool feature of checked exceptions. It really lets you track down where you need to deal with that error somewhere. And so in main, we might do a try catch. Or we could even say main itself might throw some kind of IO exception. And I'm going to put this down here. There's actually a secret main down the bottom because Java. But if I say that the whole program might throw an IO exception, you see that now this all ends up working. If I ask to run the program, you'll see that I have in here hello.txt and world.txt, but I don't have foo.bar. And so we get this no such file or directory. If I get rid of the offending file over here, just hello and world, then it gets me the first line of each of them, hello there and world. So it's operating, as expected. So these are those two different approaches, like two more approaches to error handling, checked exceptions, unchecked exceptions. So why are checked exceptions, clearly so much less popular than unchecked exceptions? And the answer is that this is kind of opinion. This is speculation to an extent. But my opinion for it is that it comes down to language design, the design of Java itself. Importantly, it doesn't play well with other features of the language. So if I have this like this, and I have a relatively imperative approach, for writing this code, things end up working correctly. But if I change this to list of, hello.txt, world.txt like this, and I want to use a more functional approach, right? Like using the into iterator, which is stream is what Java calls that. And then say map the name of a file into the first line of that file, and then collect that into a list at the very end. So I don't know why it's formatting things so strangely. Let's even move this back a bit. I could write all this exact same code here like this. So first line's 1, first line's 2, and then print either of them out. These are equivalent approaches based on, what we saw in Rust. See how it works for the imperative version? It doesn't work for the functional version. It's saying this is unhandled. Even though my function here says it throws an IO exception, it's fine with it. The actual design of how Java implemented these, like these Lambda functions that we end up using in our functional programming, it doesn't work. We get this error and we end up needing to put a try catch in here. And this is a big criticism of checked exceptions, is that they are sort of magically implemented on top of the language in a way that it doesn't work well with other features of, the very same language. So I think a really big problem for Java, and there's actually a really interesting blog post about this exact issue with checked exceptions in Java. Remind me at the end of the lecture. I'll see if I can track it down quickly and put it in the chat. Yeah, that's I think a big reason as to why checked exceptions may not have taken off. However, I've got 20 minutes. I think we can get a lot of the benefits of checked exceptions, knowing statically when things might go wrong and being able to deal with it by virtue of some types, which is, checked exceptions as a whole are quite a bulky feature to add into a language. There's a lot of extra sort of special cases and, stuff that the compiler needs to deal with. They're not so like, I'm not as compelled to believe that they're such a fundamental construct of a programming language. And when I say that, what I mean is, like, let's say something like a struct, whatever your language calls a struct, whether it's a class or a, object, whatever, that seems like a really fundamental unit, a fundamental building block of a programming language, right? In that if your language doesn't support being able to take multiple pieces of data and turning it into one bigger piece of data, that seems like a pretty important thing to be able to do. Whether or not it's exactly structs, class, whatever, if you're not able to do that, it's probably going to be a bit painful to deal with. In the same way, like in the same way of something like an if statement, right? Or an if expression if you're a little fancy. Being able to change your control flow based on some kind of condition, right? It's not all languages need if statements, but if you're not able to, if there's no, tool for you to be able to do that kind of thing, you're probably missing out on something. And I think some types, although they're, they're not in as many languages, let's say so far as unchecked exceptions, I think they actually do represent maybe a more fundamental building block of a programming language that's been sort of, been a little like ignored or misunderstood until quite recently, where this slide needs to get updated. A lot of programming languages are trying to bake some types in after seeing their success in some other mainstream languages, even though they've been known about and understood academically for decades by this point. I think that there's something interesting to explore there. So let's do that. Let me push this off to the side somewhere and move these things back. This can run in the background. Okay, cool. And so some types are Rust's main approach to error handling. So we're going to explore that using Rust as a sort of two birds with one stone kind of thing. We, learn a little more Rust and also observe this approach a little bit. So let's try and do this same thing as the C code, but in Rust, where we're opening a file and trying to read some contents. So in Rust, I'm going to write something like this. Let file be equal to file open, right? Open file open, sure. hello.txt, like that. Now, the question is, and my text editor is trying to hide it from me. I don't know why it's... the question is, what type is this? And why it's showing the arrow, but then it's not... maybe I need to do like a dot, this thing, just try and... I don't know why it's not showing me the type. That's so annoying. Okay, oh well, it is what it is. So if I say file open over here, you'll see that I get a result back. Now, don't be fooled, like result of file, shouldn't that be an error thing here? This is a common pattern having like a type alias. Type result of t is result of t and this error type that we, is specific to IO. So the result does have two things there. It's just an alias they're using. So it specifically gives back a result. If I try and do something on a file, like let's say, like read from a file, you'll see that it will have this, read function available. And I need to use std fs read. No, std io read. I think yes. If I try and say file.read, this isn't going to work. No method named read found for result. So in the same kind of sense, we have this idea of like checked exceptions in air quotes with some types here, where we're saying this thing returns a result that may be okay or maybe some kind of error. You can't just use that as a value without acknowledging that there might be an error. Now, if I go unwrap this result and then ask to use read, I'm missing the argument here, but you're seeing that read is something I'm now able to use. So there is still a shortcut, again, for like that prototyping, trying to move quickly kind of phase, but you have like a target to track down. I'm going to hunt for all those unwraps, clean them up when I want to make my code a little more robust. So our code might look a little something like file open and then, unwrap that. Or if we're a little more robust, might end up looking like file open, and we're going to like match on that. Match on the file open. If it's okay and we have a file, then give that file back. If there was an error and there's some kind of error here, we might like to handle that separately. Maybe what we'd like to do is say, print out, like aneprintln, error, standard error print, failed to open the file, and like here's an error message, and then return out of main, exit the program. Amazingly, this actually works in Rust, even though I don't, like this case here gives back a file, and like this variable here is actually like a file, not a result of a file, but an actual file now. This ends up working even though the error case doesn't give any kind of file type back, because it returns. The Rust compiler understands that if I return from the whole function from in here, then I don't need to actually give a value back. We're not even going to get to like whatever comes next in the function. So that ends up being quite convenient, if I want to write my code a little more robust like this. Right, so if I try this out, errors, cargo run, without all these, there's warning unused, it's going on and stuff like that, fail to open the file. And then we have an error like object that we can deal with, or we can just print out some kind of debug representation, not found, no such file or directory. And then when we do have a, hello.txt, hello world, then the code just runs. We haven't gotten the first line out of it yet, but there's no error message clearly anymore. And can you put the terms algebraic data type, sum type, and product type into context? Let's save that for the very end as like there's a really interesting algebraic interpretation of structs and what Rust calls structs and enums. Oh, sorry, I wanted to look at result. What Rust calls structs and enums in terms of algebra, products and sums. But it's not something you explicitly need to understand for the course. So let's save that for like post-lecture questions. It's a really good question, and I have a decent explanation for you. Cool. Now, what else do we have to do still? If we look at errors.c, we need to get a line. So we need to say file dot, let's say, let line, or let rather mute line be equal to a new string, like this, and then file dot, isn't it my brain, read line, buff read line. It's not suggesting it, so I guess I need to use std io buff read line. What's that about? Doesn't file implement buff read? My brain. Nope, I'm just being stupid. What am I forgetting again? I'm forgetting something. this happens. I have lecture brain. Just so we don't all get stuck for ages, I'm going to just like double check what my brain is forgetting at the moment. This one, what have I forgotten? Okay, right, okay, I'm just gonna read it to a string. Okay, fine, we're gonna do something slightly different. I probably need to put this, I need to like put this in a buffered construct, kind of like with the Java thing, but we don't need to get into it. I'm just gonna read the whole file into a string instead of one line as we have here. Again, it's a lecture thing. We'd be able to do it either way in real life. Ref mute line, okay, cool. All right, and the file needs to be mutable to read data from it. All right, good enough. My apologies. Cool. So file read to string that we have over here, file read to string, reads the contents of the file into a string over here. And that returns a result itself. Right, so I can similarly match on file read to string if it's okay, you know, and it might not give me anything back if it's okay. You know, I might specifically just care about if there's some kind of error, I do something else, and so on. This error value, like, you know, I could say failed to read from the file with this error and return back maybe. Now it's worth noting, okay, yeah, whatever, it's fine. It's worth noting that this is the kind of error that I could in theory forget. We're reading into this like string variable, and if it fails, like it produces this function, read to string is going to produce some kind of error. But I could in theory forget to check that error. So if I go back to this, you'll see that I get a warning, but not a error. So there are like, you know, not just language design, but also API design ends up factoring into, you know, how easy it is to accidentally forget to deal with some kind of error, or how difficult it might be to spot it in future. So, okay, it's good that we have a warning here, but it's kind of a bit problematic that this really isn't like an error. It's something that could slip past. So again, not just language design, but also API design. This is an API that's not so robust in terms of detecting the presence of an error. So, you know, Rust gets this one. There's different competing, you know, trade-offs going on here because they want to be able to let you reuse memory instead of returning a result of the string. It's, you know, there's a couple competing concerns going on here, but I would argue that this is, you know, sure, you got something else in that trade-off, but there is this side of the other, you know, the other side of the trade-off here where it's easier to miss an error from a function like this potentially. But in any case, we've only got a little bit of time left, so we're going to keep it moving. And I'd like to sort of print that line out at the end here, let's say. Cargo run, we get the, you know, the contents of the thing. If we chmod 000 hello.txt, we get, you know, permission denied. So it's doing the right thing. But of course, if I forgot to do this error handling over here and just did this, and let me actually make it clear that this is printing out here by writing the word line. 000, yeah, as it was there. Oh, it's going to fail to open the file. So I'd need to craft a more specific example where it only can't really read from the file. Of course, we can always go to like read to string. We can go to documentation to see the failure cases. We can see the failure cases in the result potentially. Not valid UTF-8. That's a okay. Let's try and make that happen. Chmod 644. If I do, what's the easiest way to do this? I can just actually, here's what I'll do. This is a bit cheeky. Grab this and put that into hello.txt. This should cause us our error. There you go. See there? No error. And it just thinks, like this function just doesn't end up doing anything, right? This line doesn't get modified. It's still just an empty string. We printed out it's an empty string. Whereas if I actually remember to deal with the error correctly, in this case, then we get failed to read from the file because it's not valid UTF-8. Right, so that's sort of the idea that we're looking at here. API design factors into this almost as much as, you know, language design does. But if your language design isn't accommodating for this kind of thing. There might be no API design that even allows you to express things in the ideal way, or the API design to do that might be so convoluted that no user is going to want to use that API in any case. So interesting to think about. And importantly, this, when you use, notice how when we wanted to have this same, this same experience in say Java, we had checked exceptions, and checked exceptions were like a full feature in the language specifically devoted to error handling, right? With this whole throws going on, this throws declaration, along with other features like try catch. The interesting thing about some types is that they're not really relevant to error handling at all. Like in terms of the function, like functionally what they are. Like we can look at option here and see that option is just either none or some t. But in the same sense, in another example, we had that like car brand, which is like Toyota or Nissan or Subaru with all different pieces of data, right? It's a more generic tool. And it just so happens that that can end up encapsulating error handling within it. And the good thing, like an interesting thing, is that, again, Java, when they introduce this new feature into their language, they have to worry about maybe it's not going to play nicely with other features that we've introduced into our language. Like in their case, it was the lambda functions, like the anonymous functions that we had over Leco 3. That we had over, here, right? These lambda functions, those two features didn't play nicely together. It turns out that lambda functions, like this thing in Rust here, plays perfectly fine with some types because they're such a fundamental basic type. There's no like real surface for them to cause issues with each other, in the same sense that like, lambda functions, these anonymous functions, closures, whatever you want to call them, work nicely with structs or, booleans or strings or whatever. They just end up having less surface area, less, bits and pieces to conflict with each other, to smash heads with each other. And so, yeah, the upside here is we still get that, those static guarantees, the static checking by the compiler that we see in checked exceptions, but it's not clashing so much with the rest of the language like it might in Java. That's a big reason I think a lot of languages are starting to really see an appreciation for some types. But it's, each language is going to have different idioms, and sadly, as programmers, we can't just go, I like this thing the best. Like, I really like this about Rust, I love this about Java, I love this about C. I'm just going to use the things that I love and nothing that I hate, because we end up being, victims to whatever context and languages and tools that we're thrown into. So it's important to know how to work with all these different systems. But we're trying to, in this course, look at a subset of features. Rust ends up being a convenient language just because it bundles a lot of these interesting concepts we'd like to, investigate in this course and see how those features might help us write more correct, more robust programs, while, still keeping an open mind and considerations about all these different trade-offs in other languages as well. That's sort of what we're going for. Cool. Where are we at? See. Did I have anything in the chat? I had the algebraic stuff. That was trying to make a binary file before. Was there anything in the previous term that I wanted to talk about? Who knows what was going on here? Let's be real. Oh, there is one more thing I wanted to talk about. That's right. It's something that I said I promised I'd come back to. Which is something back in this C code over here. Someone, wisely noted, or probably a couple of you wisely noted in the chat, that there's an implicit thing going on here where if you open a file, you need to remember to close it. That's a thing that you're supposed to do. It's for good reason. If your program crashes, midway through, you want to make sure that, things are sort of committed to the file system as early as they reasonably can be. This makes sure that, if your program crashes, you're not going to have some sort of data loss event, and also helps you make more effective use of your resources. But how do we know that we had to do this, right? Like, again, there was no warnings if I forgot to. And it's not just because compiler developers hate us and they want us to write bad code. It's because it's really difficult for them to detect whether we have or have not successfully closed a file. They would end up with so many like false positives where it's saying, hey, you forgot to close the file, but you really did close the file. And that gets really annoying really quick. False positives, compiler engineers really try and avoid. So the answer is, you really need to know, like, look at the documentation of Fopen and, you know, look for some documentation telling you, hey, you got to remember that you need to, like, close this file. Or you just have to be, like, a wise enough engineer to know I open a file, I need to close it. Or I malloc some memory, I need to free that memory, right? There's a lot of things that, you know, you have access to this thing, you need to do something to clean up after yourself. You know, even if you're familiar with concurrency, things like mutexes, you lock the mutex, you need to unlock the mutex. And it turns out language design might be able to help in cases like this as well. Specifically, I talked about this a little bit previously, but in the idea of, you know, we need to do something not 0 times, not 2 or more times, but exactly once. The ownership system in Rust ends up being really convenient to express the idea of, I want to do something exactly once, because each value in Rust, you know, each owned value in Rust has specifically one owner exactly. So notice in this Rust code here, oh my gosh. Where am I? Here. This Rust code, I open the file over here. I forgot to close it. Do I have the same problem as my C code? Do I need to write file.close or something like that? The answer is no. I am closing the file. The file is being closed because there is a trait implementation on a file object called drop, which is not popping up because it's going to be inside a thing in here, fsimp, and like it goes a little bit. Again, the Rust standard library ends up being really difficult to use as an educational tool, but I'm going to try and show you. Impl drop. I'm hoping for file. How many of these are there? 13. What if I just search for drop specifically? Match case, whole words. Come on, come on, come on. Okay, well, look, I'm not going to find, it's probably going to be a little difficult to find the file one exactly, but the idea is there's this drop implementation that says when directory instead of a file, sure. When you drop this directory object, what does it do? It actually says it calls closedr. If we were looking at this exact impl for a file instead, it would be saying fclose, right? It does it for you when it goes out of scope. So when this file here goes out of scope, there's actually a implicit already, like I don't have to write this, there's an implicit drop file that's inserted here. That drop file ends up calling fclose for us. Now Rust is really one of the only languages that is able to do this, at least efficiently, without a garbage collector or some kind of reference counting system because of the ownership system. It knows it'll only do this once because this file only has one owner. I can, a bonus out owned FD. Yeah, that would have been helpful. But in any case, yeah, we get the idea, but thank you very much for that. It's going to happen exactly once. If I go back to my C code and imagine you have a function you can call called like void do something with file star file, and it does something with that file, right? We do all our stuff we want to do, and then we call do something with file and pass it in that file. My question is, do we write fclose file afterwards or not? Is this correct to do? Remember, we want to close a file, you know, we want to do this ideally exactly once. Closing a file twice can cause some issues, but in practice often doesn't end up with really problematic issues. But if this example was malloc, allocating memory and freeing memory, then, you know, doing this more than once would be a serious problem. 0 times memory leak, 2 or more times CVE, like a security vulnerability, and you're like in some really serious hot water. So the question is, do I do this? Do I write this code here or do I leave it commented out? And the answer is, well, it depends on if this function does, closes that file or not. Right? And hopefully, we're hoping there's like some documentation here that explains it, that says like, hey, like I'm closing the file. Don't worry about it. And so I go, okay, it's going to be responsible for closing the file. I don't need to close it. That's fine. Maybe there's no documentation. I have to read through it and see, okay, I see in their implementation, they close the file. I don't have to do something. I don't have to do that. But guess what? The compiler's not checking that. You are, right? The compiler has no idea what's going on. If someone's reviewing your code that you've written to do this, they're not going to have any idea what's going on. They need to go and check, okay, to make sure this code's right, I need to go track down this thing and then look at it myself and say, okay, it says it's going to, yeah, okay. And then, so on and so forth. The ownership system helps us bake this property that we are reasoning about. We're reasoning about this property as humans when we're writing, when we're dealing with things like C code into the statically checked type system. It bakes it into the types of Rust that are checked, by a machine, by the compiler, helping us make sure we don't, screw anything up. And so there's a distinction in Rust between I own the file, I'm responsible for it, versus I'm just borrowing the file. I'm only using it temporarily. You're in charge of cleaning it up. You're going to need to write the fclose. Of course, you don't have to manually write it. Rust will do it for you automatically through drop and the ownership system. But it's all being dealt with and codified in a way that the compiler understands. It's a really powerful idea, and we get more into ownership and borrowing in week 4. Just wanted to get through that bit. Cool. Okay, that's where at time. We're at 8 o'clock. So similar to with context in Python, yep, similar kind of idea. But Python, it's still possible to sort of leak things out, if you forget to do that with block as a whole. And it's similar to like Java has the same kind of idea as well. Java has try with resources. I don't know which came first out of Python's which and Java's try with resources, but it's a similar kind of idea. It's very helpful, but you of course can, forget to do it in the first place, which is what we're kind of trying to avoid, if possible, within the scope of language design. Like in this case, I didn't close the file, I didn't close the readers, and so on. I really should have like a reader.close here in this Java code. Yeah, or maybe like file.close more accurately. Or no, reader.close I think is fine. In any case. So yeah, it is similar kind of idea, but a new approach and something that I'd like us to like experiment with in this course. Cool. Other questions? We have that other question there that I'm going to get to now as well. If you're not interested in, if you don't have any questions, you don't want to listen to the questions, then feel free, head off. Hopefully, have some food, get some sleep, so on. And thank you for coming. Otherwise, again, as usual, I'll stick around and answer questions as long as you got them. Let me also just push this code up. This stuff is all junk. Get out of here. This we don't need. What? Didn't I? Oh, right. Sorry. There we go. Cool. Yeah, that's all fine. Okay, let me push that up. Let go for error handling. There you go. That's all up there for you all. Thank you for the wishes. Okay, cool. Now we also wanted to, there was a question around the algebraic relation. Oh, and also I wanted to find that Java blog post, which might be a little hard to track down, but actually that might be something I do after the lecture. And if you're interested in that blog post specifically, just make a question on the forum if you're interested in it, and I'll if there's a question on the forum asking for it, I'll track it down and add it as a reply, so everyone can have it. It doesn't get lost. Now there's another blog post that I think is really quite useful. Rust struct enum product sum blog. Let's see. There's Who was it that wrote it? I'm trying to remember. No, I don't think it's this one. Oh, is it this one? Let me check. Oh no, I think it is this one. Yes. Yeah. This is a really good oh yeah, it's by Manish. Yeah, okay, this is definitely it. Manish is fantastic. That's usually the handle they go by on the internet. Look them up, follow some of their stuff. They post really high quality content. I'm going to put this URL in the YouTube chat. Yeah, I think that worked. Now, the relation here between sum types and product types is something that looks like this. So we have struct foo, which says that it has a boolean and a string, or we have a enum foo, which can be a string or a boolean. Okay. And so there's, other languages they're pulling in here, Swift, Haskell, and so on. This is why it's such a, great thing to read. Like, I'm going to give you the summarized version, but it's great to read because it pulls in so many different languages, which I love as a theory. But why do we call these structs are like product types and enums are like sum types? Now, if we look at a struct foo and it has a boolean and a U8, a U8 is a number from 0 up to 255, then if we think about it, how many different possible foos are there is the question we'd like to think about. In the case of a bool, you can have true or false. There's two possibilities. So two different possibilities for X. And for Y here, we have 256 different possibilities, 0, 1, 2, 3, up to 255. Now, when we have a struct foo, how many different foos are there? Well, there's two different possible X's, 256 possible different Ys, and we need to consider the different combinations. You could have true with any of those numbers 0 through 255, or we could have false with any of those numbers 0 through 255. So in total, there's 512 possible foos, right? That's how many different unique foos that we could create. And that is the product of 2 and 256. Right? 2 times 256 gets us that 512 possible different foos. And it's what's called a Cartesian product, if you've heard that in maths as well. Foo is a boolean times a U8, right? So this is where the relation to mathematics comes through. A Cartesian product is like sort of what you get on a Cartesian plane, like a Desmos, like a Desmos here. This XY plane, X equals Y plus 2, right? There's a Cartesian plane because, I'm trying to point at the screen, but see, that tuple of two values is a product of X and Y in a sense. And now if we extend this over to enums, now we have foo as either a bool with that bool data or an integer with the U8, right? The question is, how many different foos are there? Well, it's either a bool, and that bool can be true or false, so there's two possibilities there, or it's an integer with which it has a U8, so there's 256 different possibilities. But it's not both, it's one or the other. And so in total, there's actually only 258 unique foos. And you can count them up if you're not convinced, but it's either this one with false, this one with true, or this one with one of the integers 0 through 255. So 258 possible different unique foos, coming from the sum of the possibilities of each of these fields. And in particular, it's a sum of sets is the way that it's being put here. So foo really is a bool plus U8, and they're calling it a disjoint union with a discriminator, which is how it's implemented in Rust as well. Now, so this other, there's a slight asterisk here that they talk about where if you have two different options with bools, you can't quite think of it like a set because two elements that are the same in a set are really just one element. So you have to think of it more like the first bool plus the other bool plus U8 as this sum type. So they're kind of like sets. There's a lot you can do, with set theory to understand these kinds of things, but you have to be a little careful with how you apply it is what they get to there. So Rust and Swift enums are sum types because for sum types, the number of possible values is the sum of the number of possible values of each of its component types. And then they get like even more crazy. So there's the terminology algebraic data types is just talking about sum and product types together. A language with algebraic data types will have both sum and product types. Almost every language will have product types. Sum types, not as common, you know, in the last few decades, but are starting to become more and more common each passing month. And then they get even crazier with it with exponential types, and I'll let you, you know, go into all this, a pi type, and you know, this is where it gets really quite complex. I really recommend you go and read it if you're interested in this kind of thing. But that's my like Cliff Notes version of where that terminology comes from, without going into all the depths of like you know, the mathematical mechanics that you can apply to understanding and reasoning about a programming language mathematically. Hope that gives you like a brief insight, let's say. So are some types enums where variants can contain data, or are those algebraic data types? Yeah, so some types is that first thing that you said, and algebraic data types is the set of product types and sum types, you know, being present in a programming language. And this one, is it also because if you had, for example, U8 of U16 plus U32 making up some notation, you can kind of expand the U8 into U8 times U16 plus U8. Exactly, yeah. So there's all kinds of mathematics that ends up just magically kind of applying, where things like a lot of laws about products and sums end up extending into the programming language equivalents of sum types and product types. So things like commutativity or distribution laws that you have up there, absolutely. And that's why it's sometimes useful to think about these as sum and product types, because you can end up applying whole branches of mathematics that have already been developed on the basis of, you know, summation and products onto into our programming language work. But so is a regular enum where variants cannot store data also a sum type? Yeah, absolutely. And in that case, you can imagine over here, if I have an enum foo, which might be like foo bar or baz over here, really what they're holding is just a like, you can also imagine like that they're each holding data. You know, we've seen like string and bool and U8 and stuff like that. You can imagine one of these variants that holds no data, you can almost imagine as holding an empty tuple, right? An empty tuple represents no data. If we considered that everything needed to just have data for our ease of reasoning about it, then it would be reasonable to say that this thing just holds an empty tuple. It's what we'd call isomorphic, meaning this can be turned into this, like, you know, each way around. They represent, you know, effectively the same thing. So they're like they form an isomorphism between each other. So if I only had an enum with all of these plain variants like this, how many empty tuples are there? And the answer is there's one. Or if like, it might help you to look at it this way, how many different possibilities does this variant here have? And it's one. It's the variant itself, or it's, you know, the one empty tuple inhabitant, the one empty tuple value. And so we just sum them up. One for this, one for this, one for this. There's 3 different foos, right? If this one happened to be a Boolean in the middle, then we'd have this one here has one possibility. This has 2. This has 1. 1 plus 2 plus 1 gives us 4 total foos, right? And so that's, yeah, it applies not just to when you have data attached, but even to when there's no data, whichever way you end up looking at it to reason about this. Yeah. Really like good discussions there, and being able to sort of, yeah, expand that thinking as well, especially into some other stuff we know from mathematics. Really well done, yeah. Cool. Any other questions? I'll kick around. You know, so what do you call Rust's fairly unique feature where variants can have types? Yeah, there's not an amazing like name for it. That's why I generally just use sum types, because sum types allow us to contain contain data. Yeah, that's correct. Like in the sense where Swift, for example, has enum foo, case stir with a string, case boolean with a bool. Haskell has the same thing, data foo equals B with a bool or S with a string. Like this in Haskell is literally, that is, you could directly translate that into Rust by saying struct foo B bool S string, like that. And so generally the terminology that people use to describe this system of having enums, well, some kind of construct where you can store different possibilities, each with their own different potential piece of data, would be, I think the most widely accepted terminology just happens to be sum types, which is why I refer to them as that over here. There's not really a good other terminology that I'm super aware of, because Haskell just calls it data. Swift and Rust call them enums, which, you know, enums have other meanings in other languages. And C, you know, like has unions, but unions are sort of like almost a sum type, but you also need this discriminator, which comes like with this extra work over here. So yeah, generally sum types is the general terminology. Yeah, but sorry. Oh, so what I may have interpreted your original question incorrectly, where you said, so a regular enum where variants cannot store data also a sum type. What I should clarify in saying is that in a language where enums are sum types, like in Rust here, this is still a sum type for sure. But in a language where enums don't represent sum types, like in Java where we have enum foo, and you can have like A, B, C, but you can't have like A with a string. That's not valid Java. This enum is not a sum type. Or like you can almost consider it like a specific special case of a sum type, but it's not like the fully fledged feature of sum types that we had come to expect, you know, that we're sort of thinking about, reasoning about over here. I think I might have just interpreted your question from the opposite direction, assuming we're still operating in Rust specifically. Maybe that might have answered it a little better. Ooh. Any more questions? What did you think of the group by? I must have missed that in the chat. It's Itertools is a cool crate that provides extensions to iterators. Maybe my YouTube chat. Or I'm sorry, we need max of each groups.len. I think my YouTube chat, I'm not seeing a thing about group by specifically, but maybe like my YouTube chat has been known to sometimes just miss a message every now and then, but I know what you're talking about specifically, which is why I was like, there's a message about Itertools, that must be it. But there is something in here called group by, and this basically like just blows our problem apart. blows the solution, like what we're trying to achieve apart. It's really like the perfect tool for what we're trying to do. And I think in a previous term, someone asked about this as well, and I think, yeah, we have demo with Itertools in 23T3, which I think goes zip X and Y together, map into where they're equal, and then group by. And then we're just doing like filter where it where this first element exists, find the count, find the max, unwrap, or 0. Yeah, and this is like a hardcore super functional solution. It's very cool. Yeah, like super functional. I even wrote it the exact same way back then. And yeah, that's totally a valid approach as well. Itertools is a massively powerful crate. And for anyone who doesn't know it, Itertools exists in like so many different programming languages. People tend to use this specific name Itertools across many languages to basically mean, you know, your language has an iterator type. Let me add a whole bunch of even more functionality onto that iterator type. past those like 80 methods in the standard library, add another 120 on that is also still just implemented with type item and next. So you implement the type and the one next function, and now you get like 200 methods for free. So this ends up being really helpful and has, you know, all kinds of cool stuff. Like I just saw, if you want to find, I see it here, like permutations, for example. Like if you have the integer range 5 to 8 and you want to find all the permutations of length 2, 5, 6, 5, 7, 6, 5, 6, 7, 7, 5, 7, 6. You know, there's all kinds of really cool tools within here to, you know, even level up your iterator's capabilities. Yeah, really, really, really cool. Awesome. So it will be really easy to do MapReduce. So in terms of like with iter tools, yeah, you get so many more, so many more functions available to be able to, you know, work in a iterating pipeline, doing things like mapping data and, you know, reducing it down at the end. But yeah, Rust is a language that it's quite convenient generally to write things in a MapReduce kind of style, you know, across a single data set in a one like running program. Once you're running across like doing like what you might consider a typical MapReduce across like hundreds of machines and that kind of thing, like a really distributed systems MapReduce, you know, the individual languages tooling is not quite as important because, you know, you're sort of thinking on a grander scale than just one programming language might operate in. But, you know, Rust, I think, would be relatively conducive to that as well, but it's just not so language dependent once you scale up to the distributed systems vision of something like, like a Dizzy Systems MapReduce potentially. Yeah. Okay, cool. I think the questions have pretty much slowed down now. So thank you, everyone. As always, if you come up with any questions later, or you're watching the recording and you want to ask any questions, the course forum is a great place for that. If you want me to track down the blog post I mentioned earlier, just make a post on the course forum and I'll keep an eye out for that. Otherwise, I hope you enjoy your workshops this week. And I'll hopefully, assuming things are fine and I don't get worse, I'm planning to see you all again in person, Monday, Tuesday next week. Cool. Thanks very much, everyone, and have a good night, and see you later.